Good morning, good evening, good afternoon. Welcome to all those who have logged into this Knowledge Insight sessions. Today's topic is really interesting in terms of, while this is a very, I would say, generic topic, but there are a lot of things which have been mentioned specifically around this. We all know machine learning models. We all know developing machine learning models. We know around the challenges, the ins and outs which come around the machine learning models, but it's an important thing to look into what have been the patterns, what are the patterns, and on the other side to also look into what are the anti patterns when it comes to talking about machine learning models. So that's an important aspect, and to cover that we have an expert in the industry. We have Tuhin Chattopadhyay. Tuhin carries 20 years of experience in academia industry in the field of AI analytics across, I would say, across the globe, including North America, Southeast Asia. He has been part of different organizations, including Nielsen and others, and also he has been what we call recipient of numerous prestigious awards in the AI analytic arena. He has also served as the professor of practice at Jagdish School of Management, JAGSoM, just to mention, as the full form in Bangalore, which is ranked as the 14th private business school in 2022. Apart from this, he has also been invited for different talks, keynotes, speeches around different aspects around the overall data science concepts. Welcome, Tuhin. I, along with the audience, are really looking forward to your session on this specific topic, a very interesting topic around patterns and anti-patterns for developing machine learning models. Over to you, sir.
Thank you so much. Thank you so much, Kapil. Deeply appreciate all your kind words and introduction. Let me share my screen. I hope that would be visible. Yep.
Yeah.
So let me walk you through something very interesting. Uh, Patterns and anti-patterns for developing ML models. This is a highly technical subject, highly technical area, but I shall try to make it as non-technical as possible so that even if you are not into ML, if you are new to the subject, new to the area, still you can appreciate it. So that's one of my goals of introducing or taking you or walking you through this journey. Uh, my intro has already been given by Kapil. So currently, I'm serving as professor of practice of AI analytics, blockchain at JAGSoM, and also I drive my own consultancy in the space of AI analytics, blockchain, data engineering, data science, so the entire industry 4.0 for that matter. So without doing much of a ado with this introduction part, let me come to the content straight. So we are going to start with the intro, where we are going to cover ML and predictive analytics fundamentals, the first thing. Then we are going to cover the challenges in machine learning. Then you will understand the design pattern fundamentals, that what are design patterns, why it is important, the origin part. After that, we will dive deep into the area, the core part of this presentation. What are the different types of patterns and what are the different types of anti-patterns? And finally, we will conclude with the ML techniques to detect anti-patterns, the role of explainable AI, and anti-patterns to avoid ML ops mistakes. So this is the entire content. I shall try to make it uh, easy to understand, and we'll of course take the questions once the presentation is over. So the fundamentals, the first thing. So what are the ML fundamentals or the machine learning fundamentals? The algorithms learn patterns in data and use those patterns to make predictions or decisions. There are several types of ML algorithms, including supervised learning, unsupervised learning, reinforcement learning. You must be knowing that in supervised learning, what we do, that the algorithm is trained on the labeled data to learn a function that maps input to output. Say, for instance, any form of classification model, right? Say, whether a customer is going to be with the organization or not going to be with the organization. We can label them And then we can develop the models, a classification model with several ML algorithms which we'll learn. Uh, and you must be knowing already. And we can develop the model around it. And there can be unsupervised learning model as well, where the algorithm tries to find patterns in unlabeled data without any predefined output variable. So that can be a kind of, factor analysis, cluster analysis, whatever. We don't have a kind of DVI relationship, but then we try to find patterns, and then we either cluster them or dissociate them. We can play with the data. And in reinforcement learning, the algorithm learns by trial and error in an environment to maximize the reward function. So we can penalize it, give it reward so that it starts working, operating in the desired manner, and gives us the maximize or maximum reward function. So the common ML algorithms include linear regression, logistic regression, decision trees, random forest neural networks. A thought may cross your mind that, yeah, these are all statistical techniques. What is so machine learning about it? The beauty of machine learning on the top of the statistical models is that through iterative procedures, through iterative process, we constantly uh, keep fine-tuning the models so that the accuracy of the model increases. Of course, with a very clear understanding that the it shouldn't go for overfitting. So these are the kind of ML fundamentals. Now we will move to the predictive analytics fundamentals, which goes, of course, hand in hand. But it involves using data, statistical algorithms, machine learning techniques to make predictions about future events or behaviors. Predictive analytics can be used in a wide range of applications, including business, healthcare, finance, marketing. And the goal of predictive analytics is to identify patterns and relationships in data that can be used to make accurate predictions. Common predictive analysis techniques include the regression analysis, time series analysis, clustering, classification. It can be used for a variety of tasks, including forecasting sales, predicting customer behavior, detecting fraud, and identifying at risk patients if we are doing in healthcare. So that's what we can predict. Now, we will slowly move to the challenges. Because see, this purpose of the presentation is not about to give you the what is ML or the ML 101. No, we will come to the design pattern, but to understand and appreciate what are the design fundamentals, we need to understand the challenges in ML. So once we'll understand the common challenges, then subsequently we'll understand what are design patterns and how they can be applied on these challenges to mitigate them. So, what are the common challenges in ML? So, the first challenge is the data quality part, where there are multiple aspects of data quality you understand, right? Say the data accuracy. Data accuracy can be mitigated by understanding the source of the data and the potential errors in the data collection process. Data completeness can be achieved by ensuring that training data must contain a varied representation of each level. Data consistency can be achieved when the bias for each data collector can be eliminated. And timeliness can be ascertained by keeping a timestamp about when the event occurred and when it is added to the database. So these are the key challenges of data quality part. Then the other challenge comes about the reproducibility. So when we develop the ML models, it's initiated or initialized with the random values during the training. Say, for instance, the neural network models or any of the deep networks or deep learning models. That the same model code with the same training data may produce slightly different results across each iteration. That's a huge challenge, I would say. So we will understand how we can, mitigate these things when we will discuss the next section of the patterns. Then the data drift. ML models must be relevant by constantly updating the variables as the models run in a dynamic business environment. As we know that business environment constantly changes and rapidly changes at a rapid pace and that too constantly. So we need to constantly update our variables. Otherwise, there will be a drift in the data. The next important part is the scale. Now, the scale can be addressed by each of the roles, each of the key roles of a data science project, like data engineers, ML engineers, and data scientists. They're the three key roles, and what kind of roles they play in the project about the scalability part. So, data engineers need to build data pipelines that can scale to handle the big data. ML engineers need to ensure the right infrastructures like processors for seamless training of our models. And data scientists need to be served with the right infrastructure support for continued scoring of the models. So that's how these three guys or these three teams, I would say, come together and play their role, should play their role for the scaling part. And last but not the least are the multiple objectives. So, whenever we are developing a model, multiple teams using a model in an organization might have different expectations and objectives from a model. So, how we can address that challenge so that it serves the multiple purposes or at least some common goals. So, with that understanding of the common challenges of machine learning, let's understand what are the what are design patterns for that matter, and what are design patterns for machine learning to be more precise. So, design patterns provide established best practices and reusable solutions to the common machine learning challenges. So, what I mentioned, established best practices and reusable solutions. So, those things we are going to discuss, and you can again subsequently apply in your projects. So, it provides common solutions to common problems with reusable abstractions and common terminologies. So, that's what we are going to discuss throughout the next 45 minutes. So, that's the quick intro, I would say, about the origin of the design pattern. Interestingly, this has not at all been originated from either from analytics, machine learning, AI, or even from software engineering. This has started or initiated architecture. It's the when I'm saying architecture, don't think that I'm talking about the our IT architecture or the machine learning architecture. I'm talking about the real development of the buildings or those kind of architecture, the construction level. So Christopher Alexander in the late 1970 documented the design solutions as patterns through his seminal works of pattern language, towns, buildings, construction in the context of architecture. In the first half, so subsequently in the first half, the 1990s, the Gang of Four, what we commonly say, which includes our Eddie Gamma, Richard Helm, Raphael Johnson, and John Visits, they came and they designed or rather applied the design patterns in the field of software engineering with their almost 23 documents they have studied, and then they wrote the design patterns elements of reusable object oriented software for the object oriented programming. At a much later stage, in the later half of 90s, the concept of anti-pattern was introduced in the software engineering, and subsequently it's adopted in the machine learning. So that's the kind of a brief history of this pattern and anti-patterns. So, what are the fundamental design patterns? So, we will dive deep further, but just a kind of a brief intro. The first part is the data pre-processing. This pattern involves the cleaning, transforming, and preparing the raw data to make it suitable for ML algorithms. Feature representation. This pattern involves selecting the appropriate representations for the input data to capture the underlying structure of the data and makes it suitable for machine learning algorithms. Model selection. This pattern involves selecting the appropriate ML algorithms for a given problem. And of course, that choice depends on the type of data, size of the data set, and the performance metrics. Model evaluation. This involves evaluating the performance of the ML model on a held out test set. And evaluation metrics includes our accuracy, precision, recall, F1 score, area under the receiver operating characters, ROC curves. So those are the model evaluation techniques. Model tuning. involves the tuning the hyperparameters of the ML model to improve its performance. And hyperparameters are the parameters that are set before the training process begins, such as learning rate, regularization parameters, and number of hidden layers. And finally, the model deployment, the last part, where we put it on the production environment. It involves deploying the ML model in a production environment, includes building a pipeline to handle incoming data, monitoring the model's performance, and updating the model as needed. So these are the fundamental design patterns. Now we are diving deep into the machine learning design patterns, a deep dive. The first or the most important thing we have to understand what are the difference between patterns and anti-patterns. So pattern, as we understand, is a general solution to a commonly occurring problem that has been proven to be effective in many different situations. Whereas ML anti-patterns are commonly occurring solutions to problems that appear to be the right thing to do. Very important one. That appear to be the right thing to do, but ultimately lead to bad outcomes or suboptimal results. That's the kind of key difference between pattern and anti-patterns. An ML pattern is a technique, process, or design that has been observed to work well for a given problem or task. Anti-patterns are the pitfalls or mistakes that are commonly made in development or application of machine learning models. ML patterns can help guide the development of new models as well as provide a framework for understanding how existing models work. Now, anti-patterns or these mistakes can lead to poor performance, biases, overfitting, or other problems. So we will discuss subsequently what kind of different patterns, anti-patterns, if they're anti-patterns, how we're going to mitigate them. So with these models, we will discuss subsequently. I hope this is clear. This is kind of the basic understanding between pattern and anti-pattern. So there are multiple patterns and anti-patterns, but we are going to discuss only the top five patterns. The top five patterns are data representation, problem representation, model training, resilient serving, and reproducibility. And anti-patterns, the phantom menace, the sentinel, the hulk, the lumberjack, and the time machine. So what they are, how we can mitigate those challenges, we are going to discuss now. So the key patterns, as we said, data representation, problem representation, model training, resilient serving, reproducibility. So these are the five things we are going to discuss. So first one is the data representation design patterns. It refers to the common techniques and strategies for representing data in a way that is suitable for learning algorithms to process. Very important thing. Again, I'm mentioning the crux part. It refers to some common techniques that we will discuss. What are those common techniques and strategies? But what is the purpose? Purpose is to represent data in a way that is suitable for the learning algorithms to process. So how I can make the data or the ingredients, how I can present the ingredients in a manner that is easy for these algorithms to process. Easy means what? Effectiveness will increase if I put the ingredients in a manner that can be processed easily. So design patterns help to transform raw input data into a form that can be more easily analyzed and understood by ML models. A clear analogy that crossed my mind right away is, say, for example, cooking. Now, how should I prepare? Should I give the raw ingredients for the cooking straight on the pan, or I shall prepare something out of those raw ingredients and then I can put it on the pan so that my cooking gets more delicious. So the same thing, the process remains exactly the same. So you do number of things like feature scaling. So that technique involves scaling input features to common range, that is between 0 and 1, to avoid large discrepancies in the feature magnitudes. So that's the feature scaling. Again, with the input data we are playing here. What does feature scaling does is help to improve the convergence rate and accuracy of the learning algorithms. That's what the goal is. That's what we're trying to achieve. One hot encoding. What is one hot encoding? One hot encoding is used to present categorical variables in a numerical format. Very important. Uh, since we are applying the ML models, we need to convert, we need to transform the categorical variables to what to kind of numerical data. So this technique involves representing each category as a binary vector where only one element is on and the rest are off. So that's how we are doing the one hot encoding. Text representations. Text data can be represented in various formats such as bag of words, which represents each document as a frequency vector of individual words. Other techniques include term frequency, inverse document frequency, TF, IDF, and word embeddings. Then there is time series representation, can be represented using techniques such as sliding window, which involves dividing the time series into overlapping windows and representing each window as a feature vector. And image representation. Image data can be represented in various formats such as pixel values, color histograms, or CNN features, convolution neural network features. So that's how we should represent the data for design patterns. I'm sure it's clear to you. The second one is the problem representation design patterns. So, strategies and techniques used to represent a problem effectively in a way that can be solved by a machine learning model. So, again, I'm repeating the crux. What is the crux here? I have to represent the problem in a way that can be solved by the ML model. So, there is a kind of bit of a trick that I should design it in such a way. The problem should be designed in such a way so that it can be solved by the ML model, not that any problem can be solved. That if there are some particular tricks that we have to apply here. So one very common technique is the feature engineering, is the process of selecting and transforming raw data into features that can be used by a machine learning model. Then there is dimensionality reduction. So there are multiple dimensions, is the process of reducing the number of features in the data set. Resampling is the process of balancing the class distribution data set. It helps to improve the performance of the model when there is an imbalance in the class distribution. The choice of problem representation design pattern depends on the specific requirements of the problem, such as the type of data, the size of the data set, and the available computing resources. Third pattern is the model training pattern. It refers to the common strategies and techniques used to design and train ML models effectively. So, the techniques used for the training partner. So, these design patterns are intended to improve the performance, scalability, and interpretability of the ML models as well as to reduce the risk of overfitting and underfitting. So, what are the model training design patterns? Like the cross validation technique assessing the performance of a ML model by partitioning the data into the training and validation sets. It helps to reduce overfitting, that I told you in the beginning itself, and ensures that a model can generalize to new data. Regularization is a technique for reducing overfitting by adding a penalty term in the loss function of the machine learning model. Regularization helps to ensure that the model does not memorize the training data and can generalize to new data. Ensemble methods. Ensemble methods are a technique for combining multiple ML models to improve the performance. To ensemble, multiple ML models are combined together to improve the performance. So typically, the techniques are bagging, boosting, random forest that you all know. It helps to reduce the variance and improve the accuracy of the model. Then there is transfer learning, very important part. Transfer learning. It's a technique for using the pre-trained models to improve the performance of a new ML model. It helps to reduce the amount of data required to train a new model and improve the performance. And finally, the deep learning architectures. There are hundreds of architectures and they're very intricate. And maybe a separate session can be taken on only on the deep learning architecture part. That's how they generally take. Are a family of machine learning models that use multiple layers to learn hierarchical representation of the data. These architectures help to improve the performance and interpretability of the model by learning more complex features of the data. The fourth one is the design patterns for the resilient serving. Now, what is that thing? It refers to common strategies and techniques for deploying ML models into the production and ensuring that they are reliable, scalable, and resilient to failures. So, resilient serving is essential for building production grade ML systems that can handle large volumes of traffic and provide accurate predictions in real time. That's the most important part, in real time. So, what are the critical parts here? The model serving architecture. So, the model serving architecture refers to the overall design of the system that serves the ML model, machine learning model. Common architecture includes the microservices, serverless, and the containerized deployments. We all know the Kubernetes part. The choice of architecture often depends on the specific requirements of the system, such as the scalability, reliability, and the cost. The second important part is the load balancing, a very critical part of our data engineering. It's a technique for distributing the incoming requests across multiple instances of the ML model. So, load balancing helps to improve the performance and reliability of the system by distributing the workload evenly and avoiding overloading any single instance. So, that's the purpose of distributing. Then the third one is the caching. It's a technique for storing frequently accessed data in memory or disk to reduce the response time of the system. It helps to improve the performance and scalability of the system by reducing the number of requests that need to be processed by the ML model. The fourth one is the monitoring and logging. Monitoring and logging are the essential part for identifying and diagnosing problems in the system. So, common monitoring techniques include the health checks, metrics collection, and log aggregation. Monitoring and logging help to improve the reliability and resilience of the system by providing real time feedback on the system's performance and health. Failover and redundancy. Failover and redundancy are techniques for ensuring that the system remains available in the event of failure. Common technique includes standby instances, automatic failover, and data replication. Failover redundancy help to improve the resilience and reliability of the system by ensuring that the system can continue to serve a request even in the event of a failure. That's the beauty. The fifth design pattern is the reproducibility design patterns. What is that? Already I mentioned that thing in the intro. So it refers to the set of practices and techniques used to ensure that the results of a machine learning experiment or a project or a model can be reproduced by others. Very important. It is essential for building trust in machine learning research and ensuring that the results can be used in practice. So, what are the things we can do? Version control. Version control is a technique for tracking changes to code, data, and experiment configurations over time. Version control helps to ensure that the results can be reproduced by others by providing a history of changes and allowing others to track the same versions of code and data used in original experiment. Containerization is a technique for packaging an experiment and its dependencies into a self-contained environment that can be run on any machine. It helps to ensure the results can be reproduced by others by providing a consistent environment for running the experiment. Documentation is essential for ensuring that the experiment can be understood and reproduced by others. And the common documentation practice includes documenting the experiment's purpose, methodology, data sources, and analysis techniques. Hyperparameter tuning, I continuously refer to that, it's very critical. Is the process of searching for the best set of hyperparameters for an ML model. It helps to ensure that the results can be reproduced by others by providing a systematic and repeatable process for finding the best hyperparameters. And the code reliability or readability. Code readability is the essential for ensuring that the code used in the experiment can be understood and modified by others. So common code readability process includes using descriptive variable names, adding comments, documentation, even we prepare data dictionary for that matter, and following the coding standards. Now we will shift our gear to the anti-parents in machine learning. So the five key things we are going to discuss: phantom menace, the sentinel, the hulk, the lumberjack, and the time machine. So we will also focus not only about the pitfalls, but also about how to mitigate them. And that's our focus should be. It is not about pointing out the mistakes, but our strategies to mitigate those challenges. So apart from this, so from the phantom menace, typically it is the training serving skew. What is that thing we're going to discuss? But before going to what is training serving skew, let's understand where from the term phantom menace comes. It comes from the fact that this issue may not be immediately apparent. It may not be immediately apparent during the development and testing phase, but can become a problem when the model is deployed in the real world. There lies the real challenge when the rubber hits the road. So, it refers to a situation where there is a significant difference between the training data and the data that the model is expected to encounter in production. The difference can result in poor performance when the model is deployed, even if it performs well during training. Training serving skew occurs when the statistical properties of the training data are different, very important part, are different from the distribution of the data that the model is exposed to during inference. For example, if the training data for an image classification model consists mostly of the data in photos, but the model is later deployed to classify nighttime photos, the model may not perform well due to this mismatch in data distributions, obviously, right? So that's the difference. That's what we are supposed to mitigate. That's called the training serving skew. So how we can mitigate this risk for the phantom menace anti-pattern? Ensure that the training data is representative of the data that the model will encounter during inference. Monitor the model's performance in the production to detect any performance degradation caused by the distributional shift. Techniques like data augmentation, transfer learning, and model calibration can help improve the model's ability to generalize to new data. The second one is the Sentinel, which is validate model data in online environment before letting it go live. That's the crux. So, it refers to a technique used to validate models or data in an online environment before deploying them into production. A sentinel is a separate model or set of rules that is used to evaluate the performance of the primary model or data in a production environment. The purpose of a sentinel is to act as a safety net. It is casting a wide safety net and prevent any incorrect or undesirable outputs from being released into the real world. It can detect issues such as data drift, concept drift, or performance degradation and provide alerts. Continuously, it will flag the alerts to the development team to investigate and resolve the issue before it causes harm. So that's the kind of representative model. So in the offline environment, you do the model and the model publisher is there. And the Sentinel service comes in the online environment. Before you put it into application, the model loaded is there, and the model will be validated here, and the alert would be flagged if there is a kind of gap, or it will republish. So in the context of an so this is an example. In the context of an online recommendation system, a Sentinel model can be used to evaluate the recommendations made by the primary model before they are shown to the user. If the Sentinel model detects the recommendations are significantly different from what is expected, it can trigger an alert for the development team to investigate and address any issues before the recommendations are shown to the user. The third anti-pattern is the Hulk, or what we also call, or also known as, offline precompute. The Hulk anti-pattern in machine learning refers to a technique where the entire model training, vali- validation, and evaluation process is performed offline, and only the final output or prediction is published for use in a production environment. The term Hulk comes from the idea that the model is developed and tested in isolation, like the character Bruce Banner, who becomes the Hulk when isolated from others. You all know. So, how it has been done? So, validate the model's performance in a production environment and continuously monitor the data and model performance to detect and address any issues that may arise. This can include techniques such as data logging, monitoring, and feedback mechanisms to enable the model to adapt and improve over time. So, you can see in the online environment, historical data comes and then the model evaluation takes place with the generate features, predictor, decode output, data publisher, and then it goes to the offline environment with the cache, and then it's go to the application. After the application data comes to the cache, and then the output gets generated. The fourth anti-pattern is the lumberjack or the feature logging. So features are logged online from within an application, and the resulting logs are used to train machine learning models. The term lumberjack comes from the idea of cutting down trees and processing them into logs, which are then used to build the structures. Similarly, in feature logging, the input data is cut down into individual features, which are then processed and used to build a model. You can see the analogy, right? That's why the name has come, the lumberjack. So the risk mitigation for the lumberjack anti-pattern carefully design the feature logging process to capture relevant information and avoid biases or errors. This can include techniques such as feature selection, feature engineering, and data validation to ensure that the logged features accurately represent the underlying data. Validate the model's performance in a production environment, and continuously monitor the data and model performance to detect and address any issues that may arise. So, in the offline environment, the live data is there, model evolution takes place in the application, feature configuration takes place, the labels are there, and then there is the online part where the feature logs comes, and then the model training takes place. The fifth or the last anti-patterns that we are going to discuss is the time machine, the snapshot facts, and shared feature generation code. The time machine anti-pattern in machine learning refers to a technique where historical data is used to train a model, and the resulting model is then used to make predictions about the future data. This approach is also known as time based modeling or temporal modeling. The term time machine comes from the idea of using historical data to predict future events, like the concept in science fiction of a machine that allows model to travel through time. So what are the risk mitigation strategies for time machine and time pattern? Carefully design the modeling process to capture changes in the underlying data over time and validate the model's performance on recent data. There are multiple techniques that can be used, like sliding windows, incorporating time dependent features, and monitoring the model's performance over time. Now we have come to the last leg, the conclusion part, but we are going to discuss some very important things even in the conclusion part. So, what are the common ML techniques to detect anti-pattern? Cross validation, again, I'm repeatedly hammering on this part. We should, you already know about by now that what is cross validation. So it is splitting the data set into training and testing data set. For overfitting, underfitting, we use it. Bias detection is a common anti-pattern in ML that can lead to unfair or inaccurate prediction. So ML techniques like fairness metrics, demographic parity, and equalized odds are used to detect and mitigate the bias in the models. Number three is the feature selection. It's a technique used to identify the most important features or variables in a dataset. It is used to detect and address anti-patterns like irrelevant features and feature redundancy, which can lead to overfitting and reduced model performance. Model interpretability, decision trees, random forest, Lime. I'm going to discuss Lime separately in the next slide, maybe, can be used to provide interpretability and transparency to ML models. It's used to detect and address anti-patterns like black box models. Typical neural networks are said, right? But this we are going to discuss how we can illuminate the black box through the two different techniques we're going to discuss, which are difficult to interpret and can lead to reduced trust and performance. Performance metrics. ML models can be evaluated using a variety of performance metrics, including accuracy, precision, recall, F1 score, AUC, and RUC. Monitoring these metrics over time can help detect changes in the model performance and identify anti patterns like model drift and overfitting. Now, this is the very important part, as I mentioned, that how we can illuminate the black boxes, and explainable AI takes a major role there. So, what is explainable AI, XAI? Improve the design patterns and anti-patterns in ML by providing transparency and interpretability into how ML models are making decisions. Identify and mitigate anti-patterns in ML by providing insights into how models are performing and where they may be making errors or exhibiting bias. Identify patterns in ML by providing a better understanding of how models are working and what factors are contributing to their success. Improve the design patterns and anti-patterns in ML by providing greater transparency and interpretability into the behavior of ML models. Help ML engineers identify and address issues with the design and implementation of their models. Now, please don't think that these are all the kind of English lectures because they're done in the PowerPoint slides. We typically use all these Python libraries for explainable AI. So I've taken again the top six. There are a number of other libraries though. The most commonly used libraries are the SHAP or the Shapley Additive Explanations, a library for explaining the output of any ML model using the Shapley values, a method for cooperative game theory. You all be knowing how we use Shapley model, Shapley values. The LIME, as I was saying in my previous slide, the local interpretable model agnostic explanations. It's a library for explaining the predictions of any machine learning model by approximating it with a simple or simpler interpretable model that is locally faithful to the original model. That's the LIME. LE5, explain like I'm 5. So I library for debugging and visualizing ML models using a variety of methods, including feature importance, permutation feature importance, and partial dependence plots. Scatter, a library for building and interpreting machine learning models using a variety of methods, including rule-based system, decision trees, and counterfactuals. Yellow Brick, a visualization library again for MLs that includes tool for visualizing models, model performance, feature importance, and decision boundaries, among other things. And lastly, the TensorFlow explainability, a library for interpreting and explaining the predictions of TensorFlow models using a variety of methods, including integrated gradients, saliency maps, and occlusion sensitivity. Finally, we will look into the anti-patterns to avoid when implementing ML ops. So again, the same thing we will look it from the perspective of or from the lens of ML ops. So, model drift. This anti-pattern occurs when the performance of a ML model deteriorates over time due to changes in the input data distribution. To avoid model drift, regularly monitor the performance of the model and retrain it as needed. Lack of automation. This anti-pattern occurs when the ML ops processes are not fully automated, leading to errors, inconsistency, and delays. To avoid this anti-pattern, automate as much as the ML ops process as possible, including data pre-processing, model training, evaluation, and deployment. I'm sure many of you know about data robots and other kind of platforms where end-to-end automation are there for the entire data science projects. So in a minute, what used to take some 3 months, 6 months, in a few minutes, nowadays the projects can be done. Data bias. This anti-pattern occurs when the training data is biased, leading to biased or inaccurate models. To avoid data bias, carefully curate the training data to ensure that it is representative of the target population and that there is no unintentional bias in the data. Lack of documentation. This anti-pattern occurs when MLOps processes are not well documented, leading to confusion and errors. To avoid this anti-pattern, document all aspects of MLOps processes, including data sources, pre-processing steps, model training, evaluation, and deployment. Poor model selection. This anti-pattern occurs when the wrong ML algorithm is selected for a given problem, leading to suboptimal performances. To avoid this anti-pattern, carefully evaluate different ML algorithms and select the one that is best suited for the specific problem at hand. Last but not the least, overfitting. This anti-pattern occurs when the ML model is too complex and feeds the training data too closely, leading to poor generalization performance on new data. So, to avoid overfitting, regularize the model and use techniques such as cross validation to ensure that the model generalizes well to new data. So, with that, I'm bringing an end to this discussion. I have tried to explain it in as simple terms as possible, ensuring that even an individual who are not from ML background or don't have a kind of mathematics, statistics background still can understand the underlying philosophy. And those who have the background, I strongly recommend. I let me stop sharing the screen. Let me take it forward from there. I strongly recommend them to keep a close eye to these patterns and anti-patterns and implement implement the risk mitigation strategies that I discussed. That's something very critical. So I hope this is clear to you all, and it will be my pleasure to discuss any of your concerns, doubts, or questions. Thank you so much. Thank you, everyone.
Thank you, Tuhin, for a wonderful session in terms of the insights which you provided, right from talking about the overall patterns and anti-patterns, going into what we call the basics of developing machine learning models in terms of the fundamentals. I would say the challenges in machine learning, the design pattern fundamentals, right from origination to what we call the rational behind using design patterns, and then going deep into the overall patterns in machine learning, and of course the anti-patterns in the machine learning. And I'll not go into the detail which you went. Of course, you talked about different set of things there, and then you concluded on the overall ML techniques which I use to detect anti-pattern, the role of explainable AI, the anti-patterns specifically to avoid the ML ops mistakes which come in specifically. So, one question in terms of what is your recommendation for people who are specifically joining new from universities, from academic institutions to organizations? Any specific tips, tricks, or I would say recommendations which you have so that they can kind of enable their journey into the I would say, AI analytics ecosystem quickly, and but with the correctness, I would say, correctness, quality.
Would you like to give me this answer in the context of my presentation or in general?
No, I would say if you can give it in general and then kind of put it back to the presentation, some of the things can get connected to it.
Sure. Let me
That
connect
will
both
be
the
helpful.
things. Let me connect both the things. So let me start in general. One very important thing is that for the freshers who want to join the industry, is that get a complete grasp of many things. Number one is the business. Uh, don't just be a coder. Please just don't be a coder. Uh, very soon all these coding techniques can be automated, just like ChatGPT. Codes can easily be retrieved by asking a simple question: where will you go if you just be a coder? So don't come out of that shell that I know Python, I know R, therefore I am a data scientist. No, not therefore you are a data scientist, therefore you are a coder. There's a big difference. It's a big difference. So what are the difference? Number one is that have a complete grasp of the business. Business is very critical. Business means, what do I mean by business? Not that who is the CEO of which company or what is the revenue. No. Business means the business dynamics for a particular phenomenon, why a particular phenomenon is happening. If the sales is not taking place, why? What kind of variables? The business. Don't look at data first. Understand the business dynamics. That is the first thing. Second of all, don't mechanically, since you have learned that for prediction I shall use regression, therefore whatever comes to prediction I shall just plug in regression. Don't mechanically do it. Understand in much in-depth way. Do a lot of deep dive into the, even before you go to modeling techniques, spend a lot of time in data sanitization. Make the data fit, otherwise it will be garbage in, garbage out. So I find many of the data scientists come and then the model accuracy is very low because they have not done the basic sanitization. And then apply multiple techniques. I would say apply at least 10 techniques, apply at least 10 models, 10 types of models, 10 types of models for each problem. And each model will have at least 500 iterations. Then figure out the best one. That's how you should approach the whole thing. Now, coming back to the connecting with what we have discussed, a lot of things you can, take it. A lot of takeaways are there for you. So mostly in the freshers are not very, very much aware of these patterns and anti-patterns. So how to have the sentinel model in place, how to check it. Suppose you must have learned the recommendation system model that might have been taught to you, but then how to do a kind of check before you put it in the production environment, that is something it's a takeaway you can implement in your project. So subtle there are multiple nuances which I believe one will learn with experience also.
Absolutely, no, great set of. So one is that it's not important. It's not just being a coder. It's more important to know the domain. And when we talk about domain or business, it's more about knowing the business. What are the different dimensions of that business, right? How it is run. What are
Because see, ultimately it's a kind of business analytics, it's
yeah.
not just analytics. Another thing, I have another suggestion on that regard, I must say. Even for even if they can code but they don't know the logic of the algorithm, that's
Hmm.
something I think is very much missing. Suppose they will apply decision tree, but do you know what is the logic, how the model is actually behaving? Or segmentation, cluster analysis, let me call the library and put it. That's we understand how the algorithm actually behaves,
Yeah.
what is the underlying logic. Once that thing is understood and appreciated, your modeling techniques is bound to improve with time.
Yeah, makes sense. Yeah, absolutely. And uh, Tuhin, in terms of when we talk about the anti patterns, right, which you talked about, are there specific examples of companies who are using these versus the
Oh, all
other?
of them are using it.
all
No,
of
of course, of course, of course, of course. They
Hmm.
have all their measures in place. All these measures are there in any real time period. They cannot just what we just say that the cycle keeps
Yeah,
going.
yeah.
Train the model and then first you process the data, train the model, validate the model, and then you put it in the environment. It doesn't happen like that.
Hmm.
They are all there. They're all there in a very structured manner. They are there,
Right.
not in a subtle way. They are in a big way.
Hmm. Great, great.
It
No,
has to be there. I would say it in this way. It has to be there. If they
hmm,
are not there, there will be disasters. The
hmm,
prediction will be just Netflix cannot predict rightly, Amazon cannot predict rightly, YouTube cannot give the right recommendation. Nobody can do it. These are the integral part of any model development.
got it. Yes. No, great. Thank you so much, Tuhin, for the wonderful perspectives. I really enjoyed the session.
Absolutely, my
I'm
pleasure.
sure
Absolutely, my pleasure.
the audience would have enjoyed that also. We look forward in future also some amazing sessions from you.
Sure.
Thanks a lot for your time and appreciate being there in 3i Knowledge Insights. Thank you.
My pleasure. Have a great day. Great day
Yeah.
ahead.